Our first speaker is Tim Standing. Tim started as writing storage drivers as a way to pay his way through grad school in 1986. A few years later, an engineer at Apple told him that once you start writing storage drivers, nobody will let you do anything else. And that's been his career ever since. He is now VP Software Development, Mac, and leads the Mac software development team at Otherworld Computing. He's also the lead engineer at SoftRaid for Mac. Tim's favorite Apple product was the original iPhone, which he bought in Boston just after it was released. He had tried the Nokia and the Palm and was about to buy a BlackBerry, oh God, when the iPhone came out. His second favorite product, which I will show, is the ever classic 128K Mac, a product we all loved at the time. So without further delay, here's Tim.
Why is it technology never works when you want it to? Here we go. I just wanted to start my clock so I didn't run over. I'm going to start with a little, this is my talk, this is who I am. I realized when I did my practice talk, you can tell I'm a C++ programmer because there's a semicolon in the title. If I wrote more Python than C++, they wouldn't be there. So anyway, a little nerdy humor. As Marie said, I rewrote SoftRaid for macOS 10 back in the 10.2 days. I have been working on it ever since, improving it, removing crufts, removing stuff that's not needed. It's an interesting way to track the OS is to try or to actually stay up to date with the technologies and keep your product relevant. It's interesting that there are several parts or many classes in SoftRaid that really haven't changed since 2002. I don't know if that's good or not. But there are other parts of the RAID 5 code came in 2015. We're working on RAID 6, which uses the same classes that we use for RAID 5. We're working on write acceleration, and obviously AFPS support is coming soon. So my talk is divided into 4 parts. The first is a description or a brief discussion of where storage hardware started and where it's going and where we think what we're excited about in the next 12 months. The second is a revisit on a topic I've talked about many, many times, copy on write, why you want to avoid it with HDDs. Third, I'm going to cover how Apple is making startup volumes more and more secure with each OS release over the last 3 or 4 OS releases. That is, I'm really curious to see what they're going to change next week when WWDC comes. And the last is what Apple is doing to change the macOS driver model and how that will make things more secure as well. So the first thing I want to do is do a brief review of storage hardware. You may recognize this, right? It's what we used to connect our parallel ATA drives to our Macs with. And you'd sort of swirl around inside your Mac and plug in 1 or 2 devices and hope that everything is right. And when you think about it now, it seems pretty antiquated because we have so many wires here, and each wire has to be terminated by a resistor and a transistor that's going to turn it into a signal that the digital hardware can then support and use. And there's all sorts of noise and stuff that gets generated on this, and you really have to, if the cable is in the wrong place, et cetera, things didn't work so well. It couldn't go very fast. So people came up with the idea of doing it over just a couple cables, hence serial ATA or SATA. And everyone sort of, certainly I did in the storage field, breathe a huge sigh of relief when we could dump those ribbon cables and have something where if it plugged in, it usually worked. If it didn't work, the drive was dead or something was wrong with the drive. So we then have sort of where we've been for 15 years, say, SATA drives. So they've gotten faster. They sort of clocked out or stopped getting faster at the 6 gigabit per second, which works out to be roughly 500 megabytes a second. They have gotten significantly larger. This is, I bought 4 of these for testing 2 years ago. They were state of the art, 10 terabyte. Now they're old hat because we're selling 18 terabyte drives now. As with, SATA rotating disks, hard disks came along, so we started to see SATA SSDs, and these were killer because they could actually saturate the SATA bus, right? You can do 500 megabytes a second on one of these, and it seems like it's screaming. The problem is, as you want to make a laptop smaller and smaller, what happens is you realize that there's a lot of air in here and a lot of metal that you don't need in a laptop. There's an additional problem, which is all your CPUs now are talking PCIe, and those PCIe lines go to a SATA controller. Usually it's 1 or 2 lanes. Even if it's only 1 lane, it's a gigabyte a second. If it's 2 lanes, it's 2 gigabytes a second. That's going to a controller chip. You're getting a fourth of that bandwidth over SATA. The rest of it is just like lost. You can't use it for anything. And then you get out to the other end, and there's another SATA controller chip that takes your SATA to another bus inside one of these devices. And the flash memory isn't actually all that fast. What people do is they basically create the equivalent of a stripe inside each of these. So they have multiple banks of flash, and they use them in parallel to get the speed up. So they're pretty, they're not working very hard at 500 megabytes a second. So very quickly, people realized you could make a card that had no SATA on it that just spoke PCIe. And that's what this is. This is an NVMe blade. They were incorporated into Macintoshes for several years. Now the chips are just literally soldered on the motherboard with the PCIe interface directly in. But this was sort of the transition. And the cool thing about this is we can build external storage devices with these, right? We can put them in a device like this, which we sell called a Thunderblade. It has 4 of those blades in it. It's completely silent because it just has this giant 70s stereo looking heatsink on it. And we sell a lot of these to people on movie sets because they make no noise. They work all day long. They work in the heat. They work all over the place. We are just starting to ship these with 4 8 terabyte SSDs, so 32 terabytes, which is pretty cool. But the problem also is that you don't want one of these guys sort of lying around. You don't want to have some enclosure where you're plugging and unplugging these because they're static prone. If you sit on it or dropped it, it would probably stop working. The 8 terabyte ones are going to be pretty expensive. So you want to have something that's a little more protected. And for that, we're using a new standard that's been used in the data center quite extensively. We're moving it into the Macintosh market. OWC is primarily a Macintosh company. We've been around for over 30 years. We really champion the Mac market. And we brought a lot of really cool first to market products, the Thunderblade being one of them, U2 being the other. So this is basically that blade inside what looks like a SATA enclosure. And it's a slightly different connector, but it speaks, it's got 4 PCIe lanes on it. So it theoretically could do almost 4 gigabytes a second. In practice, they do about 2.5. But they're killer because you can just sort of plug them in, treat them like a hard drive, not worry so much about them. The other solution we have is this device, which is a 3.5-inch U.2 enclosure that takes 4 drives in it. So again, you can RAID these together with soft RAID. You're going to get, if it's internal, you're going to get 6 gigabytes a second. If it's in a Thunderbolt enclosure, you get about 2.5. Okay, I'm going to go back. I'm going to be jumping back and forth between sharing and not sharing, so you have to excuse me. Okay. So another product we've sold a lot of since the new Mac Pro came out is the Excelsior Form 2. It's basically a Thunderblade, but instead of having being an external enclosure, it sits inside the Mac. Because it's directly on the PCI bus, it'll reliably do 6 gigabytes a second reading and writing. It comes in size up to 32 terabytes, no fan. Usually we sell one of these into a movie studio, and then we sell a bunch more. People also use them for Photoshop, for rendering, all sorts of things. And we've been really successful with them. We obviously have follow-on products that I can't talk about that are similar, but we're really excited. They will work on the new Apple Silicon Mac Pro whenever that comes out. So anyway, we're excited about it. For people who want just raw storage, 8 18 terabyte drives gives you over 100 terabytes of storage, RAID 5. And this is sort of the economical way to do that. It's really a pretty hefty piece of aluminum. You can, it's going to stand up, is what I should say. It's got a PCIe 3, actually 2 PCIe 3 SATA controllers in it, and it comes with soft RAID, so it'll do RAID 5 or RAID 4 or RAID 1 plus 0, whatever you want. The cool thing about doing things in soft RAID is you can take 2 of these enclosures and do a 16 drive RAID 0 or a 16 drive RAID 1 plus 0 and put all the drives for the primaries in one enclosure and all the drives for the secondary in the other. And then you really have something that the hardware RAID vendors don't have, which is completely dual redundant setup where if one whole enclosure goes down, your data is still there. Lastly, we have a product that's sort of a jack of all, the Swiss Army knife for videographers. It takes 4 U.2 drives in the upper slots. The slots can also take SATA. The connector, U.2 connector will accept SATA, but not vice versa. The bottom 4 slots take SATA or SAS disks. It has DisplayPort. It has a PCIe slot. You can put a 10G Ethernet adapter in. And it's really, people like it because it's got so many features. I tend to like the one-trick Pronies because I don't have need for CF slots and everything else. I just need storage. And the last thing we have is this device that will take 2 of the U2 shuttles that I showed you that take 4 blades. So you'll be able to put 64 terabytes of solid-state storage in an enclosure with a really quiet fan in a enclosure smaller than a shoebox. So this should be available. We should be shipping U.2 drives within the next 30 to 60 days, and this device will be shipping at the same time. So now we're going to go through the copy on write problem. I was really excited when I heard about APFS and really excited when I started using it. And then I realized when I started thinking about how it does writes and copy on write, it's really conservative about space, but it actually can lead to some incredible fragmentation. Fragmentation has no effect on SSD, but on a HDD can have a huge effect because if you're reading part of a file here and then the head has to swing, this rate that mechanical arm can come over, even on the fastest hard drives, is still like thousands of times longer than the amount of time it takes to go to a different part of an SSD. So that we'll walk quickly through the difference between APFS and HFS when writing to a disk. So the example I have is a video file from my daughter's birthday. It's got 2 extents. It's got 2 areas on the disk that have data. Each extent has an offset and a length. If I then go and copy that file, I have to use another 10 terabytes, the volume. The data actually gets read off one place, written to somewhere else. In this example, the copy also has 2 extents. It doesn't have to. It can have 1, it can have 4, it can have any number, but this just was what came to mind when I made the diagram. If I do edits in the first original file, nothing changes. Each file still has 2 extents. I have 1 head swing if I'm going to read the whole thing. It's pretty efficient as far as not messing things up. APFS, you can tell it was written and designed with SSDs in mind, and nobody thought about this problem, and I've been trying to get Apple to give us a backdoor so we can turn off this feature ever since macOS 10.13 came out, and so far no luck. So With APFS, I've got my original file, same two extents. I make a copy, and now the copy is sort of like having a hard link to the original file. It's got pointers to the exact same data on disk. When I go and write to the original file, I then have every piece of data that I write now has to go to a new place on the disk. So in this case, I've written 4 places. The 4 places add 4 more extents. But look at what happens to the original extents. The original extents get broken into 3 clumps. So I'm now, if I'm going to read the file from the beginning to the end, I read the first part of the first extent, then I move the head way over to get the first additional extent. Then I go back to the original extent, read a little bit more, then I go back and get my second edit. I'm constantly going back and forth. So if you've got a situation where you're using APFS to store a virtual machine, and you get into a situation where copy and write is invoked, your performance is going to go through the toilet really, really quickly. The situations that cause this are duplicating a file in the Finder or making a time machine backup or any type of snapshot. Any of those operations will invoke copy on write. It turns out, I think because of the POSIX standard, using CP on the command line does not invoke copy on write. I think when I looked at the POSIX standard, it said you had to generate a separate copy, literally new data on the disk. So as a test, I wrote a Python script. I do write some Python to generate discontiguous writes. And this was, as the far left, you can see this is 500 megabytes a second 4-drive RAID 0 volume. And at the end, with a 10,000 fragments, this file was reading at 70 megabytes a second. So you've gone from 500 megabytes a second to 70. It's taking you 140 seconds to read this 10 gigabyte file. I think this is hideous. I really want to start using APFS and encouraging people to use it on all volumes, but it's still a non-starter for HDDs. So let's start talking about how Apple is making more secure startup volumes. The first step they made was in 1013 when they required startup volumes to be APFS. And the reason this is more secure is, if you look down below, I have a HFS Extended Volume on the left, an APFS volume on the right. I only have the information for one file shown, but this is times 100,000 times 200,000 for the number of files you have on your disk. So the data on the actual data on the disk that is in the volume that corresponds to your file is both the file data, which in this case is a text string, and the file metadata, which is the data about the data. So this is the name, the parent directory, the length, et cetera, permissions, all sorts of things. The difference is with APFS, there's a checksum on the metadata. So if something happens where the metadata gets corrupted, APFS can say, hey, I'm not going to use that because I know it's not right. Something happened to it. It turns out that wouldn't be very useful, except that APFS also keeps the previous couple of copies of this metadata around. So if it gets corrupted, it just rolls back to the next most recent one. You might lose a file, you might lose some copy operation, but basically your volume is still intact. And this is the reason why we don't see much of a need for disk warrior and APFS volumes. We have a test that we can run in the office here where we can basically make an HFS Extended Volume unwritable and unmountable in less than 5 minutes. And it involves writing to the file and pulling cables a couple times and doing stuff like that. We can run the same test on an APFS volume. It takes maybe 3 or 4 iterations on HFS. We can run it 50, 100 times on APFS. The volume still mounts just fine. So I think the proof is in the pudding. I think they've done a really good job on making volumes more robust in terms of surviving kernel panics or power loss or cable disconnects. The next step that Apple did was with the introduction of 1015. They introduced what's called volume groups. So the goal was around this time, or in 1014, we want to make macOS as secure as iOS is. iOS has a really good reputation for being secure from malware. We want to do the same for macOS. And the problem is you can't really go around like locking files, because someone with root privileges can then go around unlocking files and messing with them, right? So they came up with this cool idea called firm links, and the idea of having two volumes that basically mounted to the rest of the operating system as a single volume. And the volumes are the read-only system volume and the read-write data volume. And these firm links are like links that go back and forth between them, such that you can go from one volume to the other in navigation. And they're, let's just review what we know about links, and then we'll understand better how firm links work. So the links that we're all familiar with are hard links, where you've got two file system entities that point to the same place on disk, or symbolic links, which are, hey, go to this path and my data's there. They're not bidirectional, because you can have many, many hard links pointing to the same data. And once you get to the data, there's no way to get back. The same with symbolic links. And they're not one-to-one. It's a many-to-one situation. So with firm links, it is actually a one-to-one. It's like a little teleporter. You know, you step on the teleporter, out you pop the other end. So you can actually you can CD from slash users, which is you know, in the system volume read only, into standing if you're on my machine. And that's obviously part of my home directory, and then /library/ you know, software data or application support software. You're now in the read-write part of that volume group. If you then cd ... to go back, you'll just keep marching back, and you'll end back up in the read-only volume, right? So you've gone both directions. It's really cool. I think it's a really brilliant solution. And it does accomplish what it's supposed to, which is a read-only system volume and a read-write data volume. So what's going on with macOS 11? The first time I looked at this, I said, what the hell are they thinking? They've got a snapshot of the system volume, and we're booted from it. It's the mount point is / it's the snapshot. What the hell? You know, why are they doing this? It's like I had to add extra code to decipher it. It was like, God, you know, there's a slice of a slice. You know, God, it's just so complicated. Well, it's actually pretty cool. In preparing for the talk, I actually got to the point where I understood it, and I'm hoping that I can get you to understand it too. So we'll start by looking at what disk-util-list shows us. If you do a disk-util-list on my machine, this is what you see. The first on the right, the left-hand side, you'll see the standard invisible AFPS volumes that get created for booting, the pre-boot, the recovery, the VM volume. On the left side, you'll see the volumes that I see. So there's a volume called U data. U is a wonderful chocolate store in Taipei that I absolutely love. So I tend to name my volumes by something I love. And every time I go to Taipei, I like bug out of work at 6:30 and go and sit there and have a plate of 4 or 5 truffles, and I'm in heaven for like an hour. It's really great. It doesn't take much to entertain me, right? So Enigma is where all my code projects are, and then the system volume, the one which has the system identifier, is actually where the operating system is. But you'll notice that it's not sealed. It says sealed broken. What the hell? If you look at the snapshot, it's sealed. What does the sealed thing mean? Well, let's go a step further and figure out what's going on. So Apple calls the startup volume in macOS 11 a signed system volume, an SSD. They wanted to actually sign the data on the disk, not just the metadata, and they wanted to use a cryptographic signature rather than the hash they were using for the metadata. So what they chose was SHA-256, and the algorithm is similar to what ZFS uses. It's each file has its own cryptographic signature. Directories have a cryptographic signature of every entity. They take all the cryptographic signatures in that directory, they concatenate them, they make a new signature for that whole concatenation, and that is the cryptographic signature for that particular directory. And you can march up the tree. So Kernels has the cryptographic signature concatenated for all the kernel files. Then that gets assigned, and that's a signature. And the library has the same thing for all its files. And system has that for everything that's in /system. And root has the concatenation of everything that's at /root. You can see then that if I open a file and modify it, the signature will get rewritten, and that change will propagate all the way up to the root signature. And they call the root signature a seal. So if I mount the volume, say I'm booted from a different volume, I mount the volume, and I write something malicious to the kernel file, it will propagate that change all the way up the system to the seal, and the seal will no longer be what Apple expects. Keep in mind that when they do the install, they know what files they're putting, they know what for the sealed signed system volume, they know exactly what that seal signature should be. And if it doesn't agree, they just say, forget it, you've got to reinstall macOS. So this is a great way of making sure that your startup volume doesn't get modified and still bootable. But what happens if you have some low-level utility that's like some piece of malware that goes to unmounted system volumes and goes and mucks with the raw disk, right? It goes and pokes bytes, goes searching for what it knows is the kernel file, hot patches it on the disk, and then you try and start booting. Well, this is what happens. The signature gets, the signature will no longer match what is in the kernel file. All the Macs with T2 chips, it turns out the read channel reads this data and computes for executables in the system, it recomputes the SHA-256 and compares it to the one stored in the metadata. And if they don't match, it won't let the OS run that executable. So this is the other way that they're preventing malicious code from being loaded into macOS. So let's lastly talk about changes in macOS drivers. Apple has this, they're trying, like every place they look, you can see they're trying to figure out how people are going to get into the system. How can we stop it? This is the whole reason we don't have drivers on iOS, right? People have said, hey, you should do software for the iPad. At first it was a joke with the iPad Pro. It would almost be, reality. But Apple's never going to let us do that. We're going to go back, not quite to the 128K Mac days, but close. macOS until macOS 9 and Windows up through Windows 95 was all operating system, all programs were in one big memory pool. So this was really easy because then your debugger could look at everything, and if you're like me and you were tasked with the idea of circumventing copy protection on somebody's some large corporation storage devices, you could figure out what they were doing, and you could write a little init that would go and patch their executable so that it would then work with things it wasn't necessarily supposed to work with, according to the people who ran the company. So, but it was also a malware writer's heaven, right? They could go do whatever they wanted. They just like sit in there, yep, we're gonna poke at that register, poke at that address, put in this little piece of code, do all sorts of things. So with macOS 10 and Windows NT came the idea, so this is just describing that, came the idea of separating each process, each program into its own user space. So what that means is when the program loads, it gets a list of addresses that it can use. If it tries to access an address that's not in its list of acceptable addresses, it causes a fault and the program quits. If some part of the operating system does that, like a driver like mine, it causes a kernel panic and the machine goes down. But in any event, neither the operating system nor the programs are allowed to reach outside their space. So this is great, right? It keeps programs from mucking with each other. It makes the whole system more stable. Instead of the machine going down like it did when we ran Jazz on our 1 megabyte Mac Plus, what will happen is you'll just get this program unexpectedly quit, and you go back and find a different program. So the problem, though, is what about the kernel? Well, the kernel is just like Windows 95 or macOS 9. there you have all this code from all these different people sharing the same space. And if a piece of malware gets in there, it can wreak havoc. We can also, there's an example, we have a driver that is a legacy driver from copy protection for some professional sound application that will go unnamed. And this driver, if it's installed in a machine with soft read in it, we almost guarantee that it's going to kernel panic. And the customer comes to us and blames us, and we go, hey, you have this driver that dates back to macOS 10.6. It just gets carried forward every time you do an update. And this is the reason you're getting kernel panics. If you get rid of this driver, things will stop. So this is a great example of some driver that's not malicious, just poorly coded, that's leading to the instability of the entire system. And Apple wants to fix both the malware problems and the instability problems because it's their reputation. So I'm going to use the network filter driver as an example. I've used the Cisco VPN driver, and so that's what I think of when I think of this step. So what they're doing is they're moving drivers, third-party drivers, out of user memory, out of kernel memory into user space. And the driver then talks to a proxy that behaves like that part of the kernel that it needs to talk to. So the cool thing is Apple requires a provision for each driver writer saying, I'm going to talk to this piece of hardware. I'm going to talk to this network interface. I'm going to talk to this file system interface. And in the provision, it's only allowed when it gets loaded, it only sees those proxies. So it can't go like reading through all of kernel memory looking for something. It can't go like you can't load a storage driver and then have it start poking at registers on the video card, for instance, or something like that, or going and looking for a cryptographic signature for your connected storage device. So I think it's a really cool idea what they're doing. They're doing it in two phases. So the first phase is they introduced the new class of drivers. The first one was the VPN, the network filter drivers. Now they're doing HBAs, PCIe cards for SATA or Fiber Channel. And next they're going to do more advanced drivers like ours. So the first phase, for the first year, it gets introduced. You get a year to adopt it. Towards the end of the year, users start getting the dialog. Anyone who uses Cisco, any Connect will have seen, which says, you need to update your driver, go to your vendor, it's out of date, yada, yada, yada. And then they're sort of trying to get the users to shame the vendor into doing the work to move the driver over. And then the second year, it's required. So I believe now in Big Sur, the VPN drivers are required to be user space drivers. From a developer's point of view, it's much, much easier to develop and debug a driver in user space than it is in the kernel. If your driver crashes, you don't take down the whole friggin' machine, which is wonderful. The other main advantage is the installation process is much easier, especially on M1 Macs or ARM Macs, and it can be distributed in the Apple Store. And now I'm open for question and answers.
Okay. Our first question is from James, which is, how hot does the Thunderblade heatsink get after a day of hard use?
Well, that's an interesting question. We did a first version of this, and I thought it wasn't quite ready to go out the door, but other people did, so it went out the door. And we found data corruption problems when it was used in Houston in August, outside. Okay, it was sitting in the sun, and the DIT said, every time I ingest, anytime after 10 a.m., I'm getting corrupted data. So we went back to the drawing board. We found a new flash vendor. We found a new flash controller that didn't use as much energy. If I run AJ system test continuously on it, gets warm. Like I can just barely feel it's warm. True, I'm in an office I'm in the Bay Area, so it's in the 70s most of the time. So in the mid 20s for you Celsius people, I'm envious, but it never gets hot. Okay, the old one used to get hot. We actually recalled all the old ones and sent our customers new ones. And ever since then, we've had no complaints about it getting too hot. It's not like, I'm trying to think of some of the early SSDs will get blazing hot, and we don't have anything now. We've switched flash vendors 3 years ago, and I have been so happy ever since. Our flash vendor now does a lot of OEM work for people who you buy products from, and you don't know that they don't make their own flash products. So anyway, I'm really happy with them. And that's why the PCI card I showed you, it doesn't have a fan in it. It doesn't need a fan. It's just got a heatsink on it, and then uses whatever airflow the Mac Pro fan drives over it, which is not a ton. It does have thermal paste or a thermal pad that conducts from the flash and the controller onto the heatsink just to get all that heat off. But there's no, we're not thermally constrained at all.
Good to know. Second question from James is, how is the secure enclave implicated in seals?
I believe it. So the secure enclave is, I did a talk on that regarding encrypted disks. I know that the enclave is where this reading is happening. I don't know whether the seal is stored in there or not. So I'm not a hacker who I don't have time actually to go and reverse engineer how all this stuff happens, but I do read most of what Apple does, and I do dig in with a kernel debugger whenever I get a chance. My understanding, I think it's like 2 years ago. It's either 2018 or 2019. There was a MacTech conference talk I did, which went pretty in depth into how APFS works, including the extents, the allocation. Why does it take 30% longer to copy a large number of files over onto an APFS volume than an HFS volume? Turns out there's another level of indirection in there, but that is also the magic that makes snapshots work, and copy on write for that matter. So it's all really interesting. I would actually have to go and reread the slides or the talk to remember exactly all the details, but if you want to know it, it's there.
Okay. Third question from James.
I apologize.
That's okay.
So what does this architecture mean for the future of malware tools?
You mean people creating malware?
Yeah.
Well, the interesting thing, so what I read a week and a half ago was there were 8 malwares that were generated since the first of the year for macOS, at least according to this article, and I think 7 of them went through WebKit. So, WebKit is the biggest lure because you don't actually have to get physical contact. It's not like the Thunderstrike which was malware that was in the Thunderbolt cables where you'd actually have to get access to the machine. You could actually get someone to go to a malicious website, and sometimes it's just going to the website, sometimes it's actually downloading something. I get spearphished a lot, and so I get lots of, Microsoft macro documents with Microsoft macros in them, or it could be that IT is filtering those out, but I get it looks like it should have a Microsoft macro in it, or Word macro. So I think that it's like an arms race. The more secure you make some part of it, the more people go and find another place to dig in. We're seeing so many people, my mom's 91, she gets calls quite frequently. We've discovered a virus on your machine, go here, and then gets walked through. You install this software so that we can have a look at your machine. It's $3.99 to, that's the same as it's a similar motivation. And we're seeing a lot of malware at the corporate level now, and I think that's where the big money is, and that's what people are going after. They're tired of putting ransomware on somebody's machine and getting $3,000 when they can do just a little bit more and get $5 million.
Yes, my dad calls me every so often about the fact that his computer has been infected.
Yes, well, sometimes I know someone back in 10.4 days who actually had ransomware on their Mac, so it happens.
Fortunately, my dad calls me first.
Yes.
Mike Oliva has a question. This may not be your area of expertise, but could you explain what Apple is doing for kernel extension type things with us not being able to install kernel extensions now?
It's well, as I said, it's getting harder and harder. As someone whose product relies on a kernel extension, it's not a great situation to be in. Apple is now requires the user to okay the extension and then restart, which is fine, except there are problems with the kernel extension code, the code that actually creates this blob of kernel extensions and puts it in the secure location on the sealed volume. So there's that problem means that sometimes it loads the old version of the kernel extension, and sometimes it doesn't even load any kernel extension at all. And every time Apple has changed the way kernel extensions load, there's been a problem. And usually they fix it within 3 months. And I think because of the pandemic and the fact that everyone was working remotely, here it is like 9 months after Big Sur shipped, and we still have problems. So I'm working with Apple to try. I've got them working on one of them, trying to get them to fix the other one. I'm hoping that they don't make any changes to macOS 12, whatever they're going to call it, because historically, when they don't make a change in an OS, by the fall it'll be reliable. If you look at Big Sur, there was they say, oh, we had a 6-month beta period. Well, I couldn't load the software driver for 4 of those 6 months because of bugs. So Apple has unfortunately gotten to the point where, and this is just my opinion, where they're using the users as their beta testers. And they're using the developers as the beta testers. And I think this rush to get more features out every single year is really certainly in developers' disservice, and I think also in end users' disservice. People loved macOS 10.6, and macOS 10.6 was out for 3 years, and at the end of it, it was rock solid, and we haven't had an OS that's been out for 3 years since, and it shows. I can't remember what version of the OS it was. There was one where the Epson printer drivers for the high-end Epson printers didn't work for 6 months. It's just that you can't. ASR works great for imaging APFS boot volumes, except it doesn't work with Big Sur. Works great on Catalina, works great on everything before. We have a great tool in the office where I can take a 1015 image and make a bootable volume and boot from it in 3 minutes from our server. And I would love to do that for Big Sur. It saved me a whole mess of time,
Okay, last question because of time. What are the implications of the new userland requirements on network file system drivers?
Well, I don't know that Apple. I'm trying to think of an example of a network file system driver that is from somebody other than Apple. I did my second project was working on an APFS file system implementation for a NAS box, and it's like with Fibre Channel, there's a lot of state information you have to maintain for the connection, and I think they're inherently tricky. I would expect that Apple's going to move them into the user space as well. I certainly can't see any reason why they can't, given the fact that they're looking at doing HBA drivers and they're actively pursuing them. So I think that the latency is going to be a little higher for the userland drivers, but if they can abstract some of the processing, I think the performance will be there.